Hi, it's Professor Adam. Let's talk about the multi-electron problem in the electronic spectroscopy of coordination compounds. The origin of this problem started when we discussed the electronic spectroscopy of coordination complexes, and then we're hit with the problem of why there are three transitions visible in the absorption spectrum of a D2 electron complex, such as for this hexa-aqua-vanadium-3 complex. Solving this problem is done with the help of crystal field theory. Crystal field theory treats the ligands as simple point charges, but of course this is an oversimplification, and this major oversimplification is happening here, where we are treating all of the d orbitals as being equal in energy, which of course they are not. But before that, let's take a step back. We will treat the vanadium 3+, the D2 free ion, and assume that it is a sphere. Then we will see how those two electrons have different interactions depending on the d orbital that they are localized in. To do that, though, we need to define some terms. The first is microstate, which for us will be a specific valence electron configuration for a multivalent free ion. So one example could be one electron could be spin up in a dz squared orbital, and one could be spin down in a dx squared minus y squared orbital. We can calculate the number of microstates that we will have for a specific electron count in a spherical ion. The number of microstates will be dependent on the number of spaces. For d orbitals, this will be 10 spaces. J is the number of electrons, so for 10 spaces and 2 electrons, we will have 45 different microstates, which is 2 electrons in 5 d orbitals. Next are atomic states, which are a collection of microstates with the same energy. Going back to Boltzmann entropy indicates that the more states we will have a more stable system. The term symbol is a shorthand way to describe the electronic configuration in the molecular orbital diagram. We need to come up with a term symbol for the free ion before we impose octahedral symmetry. So there will be two components: spin multiplicity, where S is going to be the number of unpaired electrons, and L, which describes the total orbital angular momentum. So this brings up the idea of multi-electron quantum numbers, more than the 4 that we previously assumed that we had. Thus, we will need multi-electron quantum numbers. Recall that the lowercase quantum numbers define a single electron as per the Pauli exclusion principle. Here we are dealing with multiple electron ions. They will have multiple unpaired electrons, to which we will need to assign quantum numbers to the entire ion, which will describe more than one unpaired electron. So now capital or uppercase L is going to be the total orbital angular momentum of the atomic state given by capital M subscript L, which gives the total orbital angular momentum of a microstate. Capital M sub L comes from the sum of all the lowercase ml values. So each unpaired electron will have an ml value, which is summed to give the ml value for the microstate, which will range from minus L to plus L, much the same as for the single electron quantum numbers. S gives the spin angular momentum, which is defined using capital M sub S, which is also obtained in a similar way as the sum of all of the individual ms values for single electrons. Ms for the microstate can range from minus S to plus S. After that slight sidetrack, let's go back to our freshman chemistry and do the electronic configuration of the vanadium 3+ ion as being an argon core with 3d2 valence configuration, which means the principal quantum number is 3 and the orbital angular momentum quantum number L is 2. So ml values range from minus 2 to plus 2, and for a single electron, ms can only have one of two values. This is important because ml and ms can interact to give some configurations which are lower in energy and some which are higher in energy. So now, due to this Russell-Saunders coupling, we must determine every single microstate. But the good news is that once you figure out the microstates for vanadium 3+, the same microstates can be applied to other D2 ions in group 5, such as niobium, or any D2 ion. The 5 boxes shown here represent the 5 d orbitals, and we can determine one of the microstates now by putting 2 electrons in any of the orbitals. Here we have put them in the ml is equal to +1 and +2 orbitals. We have also made them both spin up. We will represent this using the notation on the right, where the big number gives the m sub L value for the first electron, and the plus gives the m sub S value for the first electron. Then for the second term, since the ml value here is plus 1, the big number is 1, and it is spin up, so the value is going to be a plus. So for this microstate, we can calculate a capital M sub L as the sum of all the little m sub L values, which is 2 plus 1, which gives a value of 3. The capital M sub S value can also be calculated as the sum of all the individual or small m sub S values. So this is plus half plus plus half, giving a value of 1. This leaves us with both the big M sub L and the big M sub S values for this D2 microstate. Only 44 more to go. The best way to do this and keep track of everything is to make a table. ml values along the top and ms values down the side. The microstate that we have already defined is this one, and we can say that it has a capital ml value of plus 3 and ms value of plus 1. What happens if we put the electrons in the same position but spin down? This will give the same ml value but a different ms value. A third option is to have one electron spin up and the other spin down, which makes sense because they cancel each other out, as plus a half minus minus a half is going to be 0. Changing which is spin up and which is spin down in this configuration will give a different microstate of 2 plus and 1 minus. Now we have described 4 microstates. If we put both electrons into this little m sub L plus 2 orbital, there is only one configuration that is possible, as one electron must be spin down and the other spin up to satisfy the Pauli exclusion principle, which gives a capital ms value of 0. This tells us that there is nothing that can go in either of the blue boxes, as there is no way to get a capital ms value of plus 1 or minus 1 when using the CMD orbital. For 2 and 0, we can have both spin up, 2 and 0 spin down, and then alternate spin up and spin down. For 2 and 0 gives us 4 new microstates. We are filling up the ml plus 2 column by putting the electrons in an orbital with an ml orbital total value of plus 2 and another with a value of 0. But of course, this isn't the only way to get capital ml values of 2. It can also be done by putting 2 electrons in the plus 1 orbital. Giving a third microstate with the ml value of 2 and the ms value of 0. And remember, it will only add a microstate to ml as 2 and ms as 0 due to the Pauli exclusion principle, as the electrons must have opposite spin if they are to be in the same orbital. Continuing in this vein, we can generate the states for ml as plus 1. And then for ml as 0. Since the table is symmetric, we have completed the hard part. After this, to get the microstates for minus 1, minus 2, minus 3, and minus 4 ml values, it is just a matter of multiplying the existing ml values for plus 1, plus 2, plus 3, and plus 4 by minus 1. So for ml is minus 4, we can just multiply the previous values we had for ml is equals to plus 4 by minus 1. So previously for ml is equal to plus 4, we had positive 2 with a plus and positive 2 with a minus. Now we have negative 2 with a plus and negative 2 with a minus. For ml is minus 3, we have 4 states. For ml is minus 2, we have 5 states, and 8 microstates for capital ml is minus 1, which gives us all 45 microstates for vanadium 3 plus D2. In a spherical state, however, so this does not include either the octahedral geometry or our ligands. Let's check comprehension.